we are going to discuss about the topic transformers. What is a transformer? A transformer is an electrical device used to transform or change AC voltage from one to another of greater or smaller value. We usually heard about step up transformer and step down transformer. So in order to increase the output voltage, we can use step up transformer, and in order to decrease the output voltage, we can use a step down transformer. Okay, so transformer is a device used to transform or change the AC voltage from higher value to lower value or lower value to higher value. Now, what is the working principle of transformer? Working principle of transformer is mutual induction. In electromagnetic induction chapter, we have studied what is self-induction and mutual induction. Mutual induction means whenever magnetic flux linked with one coil varies, EMF is induced in the neighboring coil. That is, when a varying current is passed through one coil and EMF is induced in the neighboring coil, that is called a mutual induction. So, mutual induction is the working principle of transformer. So, a transformer, it consists of two coils of insulated copper wires having different number of turns wound on a soft iron core. The electrical energy is supplied to a coil, and that coil is called the primary coil. So, input is given to a coil which is called the primary, and output is taken from the coil which is called a secondary coil. So, a transformer consists of two coils wound on a soft iron core. So, based on the arrangement used for winding primary and secondary coils, there are two types of transformer. This is the first one. This represents a soft iron core, and two coils, primary coil and secondary coil, are wound on two limbs of the soft iron core, and this type of transformer is called core type transformer. This is called core type transformer. Okay, that means this is primary coil. Input is given to the primary coil and output is taken from the secondary coil, and this type of transformer is called core type transformer, where primary and secondary are wound on two limbs of the soft iron core. Okay, and here in the second type, if primary, this represents the primary, input is given to the primary coil and output is taken from the secondary coil. This is the secondary coil. If primary and secondary coil are wound on the same limb of the soft iron core, one over the other, and this type of transformer is called shell type transformer. Okay children, so based on the arrangement of primary and secondary coil, there are two types of transformers. Core type transformer, where primary and secondary are wound on either limbs of the soft iron core. If they are wound one over the other, that type of transformer is called a shell type transformer. Most of the modern type transformers are this core type transformers, and transformers used in radio, TV, transmitters and receivers are of shell type. Now, what is the working of transformer? We know that when AC voltage is given to the primary, so consider this type of transformer. When AC voltage is given to the primary, what happens? The magnetic flux linked with the primary coil varies. Okay, when AC voltage is given to the primary, the resulting current produces in a varying magnetic flux, and the magnetic flux linked with the primary coil varies, and the magnetic flux linked with the secondary coil also varies. Okay, and hence EMF is induced in the secondary coil. So, that is the working of a transformer. When AC voltage is given to the primary coil, that produces a varying current, and hence the magnetic flux around the primary coil varies, magnetic flux around the secondary coil also varies, and hence an EMF is induced in the secondary coil. Let Ns and Np be the number of turns in the secondary and the primary, and Vs and Vp be the voltage across the secondary and primary. Now, the induced voltage in the secondary. What is the induced voltage in the secondary? We have induced EMF E equal to minus d phi b divided by dt, isn't it? Minus d phi b divided by dt, where phi b represents the magnetic flux. So, here also induced EMF in the secondary is minus, since how many turns are there? Ns be the number of turns in the secondary. Therefore, we can write minus Ns into d phi b divided by dt. Again, what is the voltage in the primary? That is also minus Np into d phi b divided by dt. So, induced EMF in the secondary is minus Ns into d phi b by dt. Again, induced EMF in the primary is minus Np into d phi b divided by dt. So here assumption is there is no flux leakage. Magnetic flux linked with the primary is completely linked with the secondary. There is no flux leakage. Here the magnetic flux in both the cases are same. Now we can write Vs by Vp. What is Vs by Vp? We can divide the two terms. Vs by Vp equal to d phi b by dt get cancelled. Here it becomes Ns divided by Np. So the formula is Vs divided by Vp, voltage in the secondary divided by voltage across the primary equal to number of turns in the secondary divided by number of turns in the primary. Here we have derived this relation based on the three assumptions, that is primary resistance and primary current are small. Okay, input region, primary resistance and primary current are small, and the flux linked with the primary coil and secondary coil are same, and also the secondary current is small. Based on these three assumptions, we got Vs by Vp equal to Ns divided by Np. So if transformer is assumed to be 100% efficient, normally the efficiency of transformer is fairly high, that is between 90 to 99%. Okay, that is a efficiency of normal transformers. But if the transformer is assumed to be 100% efficient, we know efficiency. What is meant by efficiency of any device? Efficiency is equal to output power divided by input power. Output power divided by input power. That is called efficiency of a device. And efficiency is usually expressed in percentage, therefore into 100. Okay, that is a value of efficiency of any device. So efficiency of transformer is also output power divided by input power into 100%. So if the transformer is 100% efficient, now what about the output power and input power? If its efficiency is 100% means input power and output power are equal, then input power equal to output power, isn't it? So if a transformer is 100% efficient, input power is equal to output power. And we know the formula for power is voltage into current, isn't it? Formula for power is P equal to VI. Input power can be written as Vp into Ip. Let Ip be the current flowing through the primary. And output power is Vs into Is. Is is the secondary current. Now we can take the ratio Vs by Vp. What is Vs by Vp is equal to Ip divided by Is. That is also a very important relation. Vs by Vp equal to Ip divided by Is, where Ip and Is are the current in the primary and secondary. So combining the two relations, we got the first one Vs by Vp equal to Ns by Np, and the second one Vs by Vp equal to Ip by Is. Combining, we can write Vs by Vp equal to Ns divided by Np equal to Ip divided by Is. Okay children, Vs by Vp equal to Ns by Np equal to Ip by Is. Now this Ns by Np, number of turns in secondary divided by number of turns in primary, this ratio is called a transformation ratio. Ratio of number of turns in secondary to primary is called a transformation ratio, or otherwise it is called a turn ratio. So turn ratio means Ns by Np is called a turn ratio. Now if Vs is greater than Vp, if Vs is greater than Vp, what about the number of turns? Ns is greater than Np, isn't it? If Vs is greater than Vp, Ns is greater than Np, what about Is? Is is less than Ip, inversely proportional, no? Ns greater than Np means Is is less than Ip, and this type of transformer is called a step up transformer. So output voltage is greater than the input voltage, and for that number of turns in the secondary should be greater and current in the secondary should be lesser, and such type of transformer is called a step up transformer. Similarly, if Vs is less than Vp, that means output voltage, secondary voltage is less than the primary voltage, and for that number of turns in secondary should be less. Okay, number of turns in secondary is less than number of turns in the primary, and for that current in the secondary is greater than Ip. And such type of transformer is called a step down transformer. So based on the output voltage, transformers are of two types, step up and step down transformer. Step up means output voltage is greater, and for the number of turns in the secondary should be greater and current in the secondary should be lesser. And step down transformer means voltage in the secondary should be lesser, for the number of turns in the secondary should be lesser and current in the secondary should be greater. Okay. We know efficiency of ideal transformer is 100% and actual transformer is very high, 90 to 99%. Thus, small energy losses do occur due to the following reasons. First reason is flux leakage. That means we know that magnetic flux linked with the primary may not be completely linked with the secondary. Okay, in the derivation we have taken magnetic flux linked with the primary and secondary are equal. Okay, so but magnetic flux linked with the primary may not be completely linked with the secondary, and some magnetic flux may leak into the air. So thus there is some energy loss due to flux leakage, and it can be minimized by winding primary and the secondary coil one over the other, or by using shell type transformer. Shell type transformer usually have more efficiency because flux leakage is comparatively very less. Okay, so that is the flux leakage, energy loss due to flux leakage. Second one is copper loss. So in transformer, copper wires are used as primary coil and secondary coil, and the copper wire has some value of resistance also. So when current passes through the resistance wire, some amount of energy lost as heat. And how will you minimize this one? It can be minimized by reducing the resistance. And how will you reduce the resistance? By using thick copper wires. Thick copper wires means area increases. Area increases, resistance decreases. So by using thick copper wires, resistance can be decreased, and thereby heating effect due to this copper loss can be reduced. So some energy is lost due to the heating of copper wires used in the primary and secondary coils due to the resistance of the copper wire, and it can be minimized by using thick copper wire. That is the second energy loss. And the third one is eddy current loss. We know in a transformer, soft iron core is used. Okay, primary and secondary coils are wound on the soft iron core. And the magnetic flux, alternating magnetic flux, we know that it induces eddy current in the soft iron core. Soft iron core is of some thickness. So whenever magnetic flux varies, EMF is induced and the current flows through the soft iron core in the form of eddies, that you know, eddy current. And it can be minimized by using laminated soft iron core. Okay, here also in soft iron core there is energy loss due to heating effect by eddy current, and it can be minimized by using laminated soft iron core. Okay, so these are the main energy losses in a transformer. Now we can see how the transformers are used in long distance transmission of electric power. We know step up and step down transformers are continuously used for the large scale transmission of electrical energy over long distance. Okay, so the large scale transmission and distribution of electrical energy over long distance is done using transformers. We know from the power station, voltage is usually stepped up. Okay, voltage 230 volt, it is stepped up to 10 kV. Okay, why it is stepped up? Because as voltage increases, according to the formula Vs by Vp equal to Ns by Np equal to Ip by Is, current can be reduced. Voltage in the secondary is high means current in the secondary is low. In a step up transformer, voltage in the secondary high means current in the secondary is low. Okay, so if current is low means I square RT, the energy loss is Joule's law of heating is reduced. So usually from the power station, voltage is stepped up by using a step up transformer so that energy loss by heating can be reduced, and it is transmitted over long distance. And in the substations, in the main stations and the substation, these high voltage is stepped down by using a step down transformer. Therefore 10 kV voltage can be reduced to 230 or 220 volt, and it can be transmitted in our homes and the industrial purposes. So that is the use of transformer in long distance transmission. So from the power station, voltage is stepped up by using a step up transformer, and in the substations and the main station, voltage is stepped down. Now we can do some numericals. The primary coil of an ideal step up transformer has 100 turns and transformation ratio is also 100. The input voltage and power are 220 volt and 1100 watt. Calculate number of turns in the secondary, current in the primary, voltage across secondary, current in the secondary, and power in the secondary. So we have to find out number of turns in the secondary, Ns, current in the primary, Ip, voltage across the secondary, Vs, current in the secondary, that is Is, power in the secondary. PS. Okay. So what are the values given here? So given value, given primary coil of an ideal transformer has 100 turns. Primary coil NP equal to 100. Clear? Now transformation ratio. What is transformation ratio? NS divided by NP is called transformation ratio. NS by NP equal to 100. Transformation ratio or turn ratio is 100. Input voltage means VP, isn't it? VP equal to 220 volt. Input voltage, that means primary voltage is 220 volt, that is given. Input power is equal to power in the primary coil. Okay, power in the primary coil or input power is equal to 1100 watt, that is also given. We have to find out all these values. Number 1, we can find out the number of turns in the secondary. Number of turns in the secondary, first one. Number of turns in the secondary is equal to question mark. Here using this formula, NS by NP equal to 100. NS is unknown but NP is known. No? So from the formula we can find out NS. So we have NS by NP equal to 100. Or NS is equal to NP into 100. What is the value of NP? NP is given as 100. So 100 into 100. So that is equal to turns. 10,000 turns. Okay. Second one, we have to find out current in the primary. IP equal to question mark. Here input power is given, no? Power in the primary coil. Power in the primary coil, we have power in the primary coil is equal to 1100 watt. And what is the formula for power, input power or power in the primary is voltage into current. Power equal to voltage into current. Since it is primary coil, VP IP. Clear children? And here power in the primary is 1100. We can substitute VP. Voltage in the primary is 220 into IP. Therefore, IP is equal to, we can directly substitute, divided by 220. So, it is equal to 5 ampere. So, current in the primary equal to 5 ampere. Then number 3, voltage across the secondary, VS. We have the formula Vs by Vp equal to Ns divided by Np. Clear children? So Vs is equal to, we can substitute Vs divided by voltage in the primary is 220 divided by Ns by Np is equal to 100. Therefore, what is Vs? Vs equal to 220 into 100. So equal to 22 into 10 raised to 3 volt. Okay, 22 into 10 raised to 3 volt. Now fourth one, current in the secondary, Is. Again we have the formula Ns divided by Np equal to Ip by Is. That is the formula. So substituting what is Is? Is is equal to 5 by 100, that is equal to 0.05 ampere. Current in the secondary is equal to 0.05 ampere. Then last one, what is the power in the secondary? So in the question itself it is given, it is an ideal transformer. Primary coil of an ideal step-up transformer. So for an ideal transformer we know that primary power and secondary power are equal. Power in the input power and output power are equal. Okay, so if input power is, what is the value of input power? 1100 watt. Secondary power in the secondary or output power is also 1100 watt. Directly you can write, or otherwise we can find it out. PS is equal to, what is the power in the secondary? Voltage across the secondary into current in the secondary. Using this method also we can find. So what is voltage in the secondary? Voltage in the secondary is 22 into 10 raised to 3. What is the current in the secondary? 0.05. And if you simplify, the answer is 1100 watt. So using this method also we can prove power in the secondary is same as power in the primary coil. Okay children. Next question. Calculate the current drawn by the primary of a transformer which steps down 200 volt to 220 volt to operate a device of resistance 20 ohm. Assume the efficiency of a transformer is 80%. So what are given, which steps down 200 volt to 20 volt. So voltage in the primary equal to 200 volt. Now voltage in the secondary is equal to 20 volt. To operate a device of resistance 20 ohm. So device connected in the output, isn't it? So operate a device of resistance means resistance connected in the secondary equal to 20 ohm. And efficiency usually represented by eta. Okay, efficiency is eta equal to 80%, that means 80 divided by 100. And we know what is the formula for efficiency. Efficiency is given by output power divided by input power. Okay children. So from this value we have to find out which is the value we have to find out current drawn from the primary, IP equal to question mark. So from these two values Vs and Rs we can directly find out Is, isn't it? So we have Is is equal to voltage and resistance are given, therefore current is equal to voltage divided by resistance, Vs divided by Rs is equal to 20 divided by 20 is equal to 1 ampere. So current in the secondary is equal to 1 ampere. We have to find out current drawn from the primary, and we know efficiency is equal to, we have the general formula, efficiency is equal to output power divided by input power. What is the efficiency given? Efficiency is 80%, that means 80 by 100 equal to output power means power in the secondary. Power in the secondary means Vs, Is, and input power means Vp, Ip. So what is Vs given? Vs is equal to 20, Is is equal to 1 ampere divided by Vp equal to 200 and Ip we have to find out. Now simplifying, Ip equal to 20 into 100 divided by 200 into 80, and after simplification you will get the answer as 0.125 ampere. Okay children. Next question, a step down transformer is used to reduce the main supply of 220 volt to 11 volt. If the primary draws a current of 5 ampere and secondary 90 ampere, find the efficiency of the transformer. Here all the values are given. It reduces the main supply to 220 volt to 11 volt. That means voltage in the primary equal to 220 volt, voltage in the secondary equal to 11 volt. Okay. Now the primary current is 5 ampere, secondary current is equal to 90 ampere. We have to find out efficiency eta question mark. Okay. Now we have the formula for efficiency, output power divided by input power. Output power divided by input power, and power equal to voltage into current. Here output power is Vs, Is divided by input power is Vp, Ip. We can substitute 11 into Is, 90 divided by Vp, 220 into 5. And efficiency is usually expressed in percentage, therefore this much into 100. So after simplification you get 90%. So efficiency is equal to 90%. Next question, plot a graph showing the variation of impedance of series LCR circuit with frequency of applied AC. We have to draw a graph relating impedance and frequency. In series LCR we know the graph between frequency and the current Im, the peak value of current, isn't it? So this is the graph. So the graph between frequency and the peak value of current is, this is the graph, and at resonant frequency current is maximum. This current is Im max, that we know. So the graph relating frequency and current is, this is the graph at which at resonant frequency current is maximum. Similarly we have to draw the graph relating impedance and frequency. Impedance and frequency. Similarly we can draw the graph relating frequency and impedance. Frequency and impedance which is represented by Z. We know that at resonant frequency current is maximum. That means what about the impedance or the resistance? Resistance is minimum. Okay. So at resonant frequency current is maximum or impedance is minimum. So the graph relating frequency and impedance is, this is the graph. Okay, at resonant frequency impedance is minima, and this minima impedance value is resistance R, because we know that at resonance Z is equal to, we have Z equal to root of R square plus Xc minus XL the whole square. At resonance Xc and XL are equal, no? Now Z is equal to R. So this is at resonant frequency Z is equal to R. So this is the graph relating frequency and impedance. Okay children? 3 students X, Y, Z performed an experiment for studying the variation of AC currents with angular frequency in series LCR and obtained the graphs given below. They all used AC sources of same RMS values and inductance of same value. What can we conclude about the capacitance values? Number 2, resistance values used by them. In which case the quality factor be maximum. So graph is given. So this is the angular frequency IM graph for X, for the student X, obtained for student X, then this one for Y and this one for Z. Okay, so the question is, what can we conclude about the capacitance value and resistance value? So clearly the resonant frequency omega R is same for all the 3 graphs X, Y, Z. For all the 3 graphs angular frequency omega R remains same, and we know the angular frequency omega R equal to 1 by root LC. Okay, so angular frequency omega R is same for all the 3 graphs. All the 3 graphs X, Y, Z, and omega R equal to 1 by root LC. And we know that inductance corresponding to X, inductance corresponding to Y and inductance of Z are same. Here it is given inductance of same value. All the 3 have the same inductance. So L remains same, omega R also same. So what happens to capacitance? Therefore capacitance corresponding to X, capacitance corresponding to Y and capacitance corresponding to Z are equal. So what can we conclude about the capacitance value? Capacitance are equal. Then what can we conclude about the resistance value? Second one is resistance. We know that this value is called Im max. So this is Im max corresponding to X, this is the Im max corresponding to Y, this is Im max corresponding to Z, isn't it? So which one having greater maximum current? Maximum current for X is greater, isn't it? So Im max corresponding to X is greater than Im max corresponding to Y, and it is greater than Im max corresponding to Z. So X has, the graph X has maximum value of Im max. Okay, so if current increases, what happens to resistance? Resistance decreases. Resistance corresponding to X is less than resistance corresponding to Y, less than resistance corresponding to Z. Clear children? So how can we say about the resistance? Resistance of X is less than resistance of Y, less than resistance of Z. And in third case, third one is, in which case the quality factor be maximum. That's the third one. In which case quality factor be maximum. We have the quality factor Q equal to omega R L divided by R. This is the formula for quality factor. All the 3 graphs having same value of L. Omega R also remains same. So quality factor depends only on resistance here. Resistance of which one is lesser? Resistance corresponding to X is lesser. Therefore, so since resistance of X less than resistance of Y less than resistance of Z, quality factor corresponding to X is greater than quality factor corresponding to Y and then greater than quality factor corresponding to Z. So the question is, which has maximum value of quality factor? Which has maximum value of quality factor? Graph X has maximum value of quality factor. Okay children.